Hi, today we are going to talk about improper integrals. And until now, we have learned about indefinite integrals and definite integrals. And this video will be about improper integrals. And there is another one called Lebesgue integral, which is not in our interest. We can start by defining in fact, by recalling the Riemannian integral. Let's consider this integral. If this integral satisfies these conditions, then we call it definite or a Riemann integral. The first condition is about the finiteness of interval of integration. We mean these limits, this interval. If this interval has to be finite, and also the function f of x must be continuous on this interval. If those conditions satisfied, then we call such an integral Riemannian or definite integral. Let's provide the definition of improper integral. For an integral of the form equality 1, we call it improper integral if and only if either the interval of integration, I mean this interval, is not finite, or the function f of x is not continuous or not bounded in this interval of integration. Okay, let's provide some examples. For instance, this is an example of improper integrals because its interval of integration is 0, at the positive infinity. Of course, this function is continuous on this interval, but interval is not finite. So this is an example of improper integral, not Riemannian. For such an integral, the interval of integration is 0, 1. And also we have a polynomial function which is continuous clearly on this interval. So the integration of the interval of integration is finite, and also the function is continuous, so the given integral is Riemannian, namely definite. Okay. Please neglect this word. Okay. Let's consider this integral. The interval of integration is 0, 1, which is finite, but the function 1 of x is not continuous on this interval. That's why it's an example of improper integral. And again, please neglect this word. For such an integral, the interval is 0, 2. Okay. And the function is 1 over x minus 3. Then the function is continuous on this interval. That's why it's again an example of a Riemannian integral. However, this is an example of an improper integral, or is not a Riemannian integral, because although the interval is finite, the function f of x is not continuous at the point x equals to 3, which belongs to the interval of integration. That's why the given integral is not Riemannian. Namely, it's an example of improper integral. Okay. For an integral from a to b, f of x dx, in order to be Riemannian, the interval must be finite, and also the function must be continuous on the interval. Otherwise, it's improper integral. And also, we have three subtypes of improper integrals. For instance, the first type, improper integral, is an improper integral that the interval of integration is infinite, but the function f of x is continuous on this interval. The second one is an improper integral whose the integration is finite, but the function is not continuous. And the last type of improper integral is an improper integral whose both interval is infinite and the function is not bounded. Yes, in that definition, we give an explanation of first type improper integral, as you can see. For such a type, we don't have any problem of on f of x, but the interval is not finite. Yes, and it might be of these forms. For instance, from a to the positive infinity, or from negative infinity to a, or from negative infinity to positive infinity. But of course, the functions must be continuous in these intervals. So, for such an improper integral, we have such a solution method by using limits, as you can see. So the first step is to take Riemannian integral and investigate the limit case. If this limit exists as a finite number, then the first type improper integral is convergent. Otherwise, we call it divergent. Similarly, if this integral exists, then if these limits exist, then we call this improper integral is convergent, otherwise called divergent. If the both endpoints are infinity, then we may choose a number such that C belongs to real axis, and we separately investigate those first type improper integrals. And this is important. If both two limits exist, then this integral is convergent, otherwise it's divergent. Okay, let's observe this example. For such an improper integral, its interval of integration is 0, infinity. And it's clearly this function is continuous on that interval, but the interval is, by the way, the interval is indefinite. So we may solve this interval by using limits. Okay, let's rewrite this integral as in the form. Okay, here is a simple integral. So if we take integration, we may write the minus e power minus x from 0 to t. So if we replace t and 0 with x, we obtain 1 over et plus 1. So as t goes to infinity, this term as pointed is 0. So we have a limit 1. It means that we have an existing limit. So our indefinite integral is convergent. Another example. Okay, the function is 1 over x, integrated function, and also the interval of integration is 1 the positive infinity. So this rational function is continuous on that interval, but excuse me, but the interval is infinite. So we have a first type indefinite integral. So let's rewrite this indefinite integral by using limits. Then we have a simple integral. So we may write here logarithm of x, and the endpoints are 1 and t. So we may write logarithm of t and logarithm of 1. Here is clearly 0. And obviously logarithm infinity is infinity. So our our indefinite integral is divergent because we have a limit as infinity. Okay, another example. The integrated function is 1 over is an rational function 1 over 1 plus x squared, and the interval of integration is 0 at a positive infinity. Okay, this rational function is continuous on each point of this interval. So we have a first type improper integral, and we may rewrite this improper integral by using the limit. So this is a simple integral, and it's equals to arctangent of x, which is the inverse function of trigonometric function tangent. So we may write here arctangent of t minus arctangent of 0, and here is the inverse of tangent of infinity, which is pi over 2. So we have the finite number, we have a finite limit, then our integral, our improper integral is convergent. Another example, for such an improper integral, the interval of integration is minus and negative and positive infinity, and the function is a polynomial, x. So we may write separately this integral as a sum of two different, the first type improper integrals. So for such an integral, and this one and also this one, they must be convergent. In order to obtain a convergent integral, otherwise, at least one of these integrals are divergent, then we have a divergent integral. So we might take this one, and also we may rewrite by using limits as in this equality. So a simple integral, we may write x squared over 2. If we replace x with 0 and t, and we obtain the minus infinity, which means that this one is divergent. So and not necessary to observation of this integral, then we have an divergent integral finally. Okay, if it's for example, if we had found this limit is finite, then we had to investigate again this integral also. If the both are, this one and this one, if the both are convergent, then this one is also convergent. Otherwise, it's divergent, as can be seen in this example. So we might make a mistake to write this improper integral by using limits directly, as in this note, because if we write this integral as in this note, then we obtain a real number, which means that this integral is convergent. But indeed, this one is divergent. So this is a mistake. Okay. The second type, improper integral. In this kind improper integral, we have a finite interval of integration, but our integrated function is not continuous on the interval of integration, which we call the second type improper integral. These type integrals are a bit more difficult to identify because the interval is totally finite, but the integrated function is not bounded on that interval. That's why it's a bit more difficult to identify. Let's provide an example. Before providing example, so if our integrated function is continuous this semi-open interval but not continuous at the point A, then we may rewrite this integral as in this equality by using limit. Okay. Okay, if the problem is the point B, then we may write here limit the epsilon goes to 0, a b minus epsilon f of x dx. But if the problem is a point belongs to the interval a comma b, but the c is different a and b, then we may write separately this integral as a sum of two second type improper integrals. If those both integrals are convergent, then we have a convergent improper integrals. Okay, let's provide some examples. We have an integral whose the interval of integration is 0, 1, which is finite, but the integrated function 1 over square root 1 minus x squared is not bounded on this interval, because at the point we have an incontinuity. So we may write this integral by using limit as in this equality. So this is a simple integral which equals to the inverse of sine of x. If we replace x with 1 minus epsilon and 0, we obtain the inverse of sine of 1, which is pi over 2. So it means that the given integral is convergent. If we had found these limits as the positive or negative infinity, then we could say that this improper integral is divergent. But for this case, we have a convergent one. Another example of improper integral. Okay, for such an integral, the interval of integration 0, 2, but the integrated function 1 over x3. But this function is not bounded on this interval. The problem is the point x equals to 0. So the interval is finite, but the integrated function is not finite. Okay, then we have to use limit. This is a simple integral. We may write minus power x minus power minus 2 over minus 2. Okay, and after some calculations, simple calculations, we have an infinite limit, which means that our improper integral is divergent. Another example. Okay, we have a second type improper integral because our interval is 0, 1, but our integrated function may be written as 1 over x multiply x minus 1, which means that our both endpoints they make our functions as incontinuous. So yes, as you can see, at those points we have an incontinuity. So we have to choose a point between 0 and 1 such that the function I mean the integrated function, they must be continuous. Let's choose 1 over 2. We might choose 1 over 3, 1 over 4, it doesn't matter. The only point is that the function must be continuous. I mean this integrated function. Okay. We have an integral like that, 1 over x squared minus x. We may use the method fractionation. We may write as a over x plus b over x minus 1. And here is b1 a minus 1. And we have an integral, the minus logarithm x plus logarithm, the absolute value of x minus 1. Our bonus 1 over 2 and epsilon. After some calculations, we have logarithm of 0, which equals to minus infinity. So we have a result as this improper integral is divergent. So we don't observe this one, because if this divergent, so our second type improper integral is already divergent. Not necessary to investigate the second one. And last type, improper integral. For an improper integral, if the integrated function is not continuous on the interval of integration, and also the interval is not finite, then our improper integral is called third type of improper integral. And to evaluate the third type improper integrals, we have to convert it into the first or second type improper integrals. As you can see in this diagram. Let's analyze the convergence of these improper integrals. Okay. Its interval of integration is not finite. And also the integrated function 1 over x squared is not continuous on that interval. So the given interval is third type improper integral. Okay. We may write this integral as a sum of those two integrals. Okay. Yeah. But here is the third type. Here is also third type. Here is also third type. Okay. But we may write here the minus infinity minus 1 and plus minus 1 to 0, and from 0 to 1 and from 1 to infinity. We have totally 4 different integrals, and all they must be convergent in order to obtain a convergent proper integral. So as you can see, this one is a first type, and this one is second type, and this one is second type, and this one is a first type improper integral. You can examine any one, so we can choose this one. Okay, from 1 to infinity 1 over x squared. Here is a simple integral, as you can see. and our integral is, as you can see, convergent. So, but we have to check all. If we had found this is divergent, so not necessary to check other. But in this case, if because we found it's convergent, so we have to check others. Okay, we have another integral, but this is the second type, because our integrated function is not bounded on this interval, and the problem is this endpoint. Okay, after calculations, we see that this integral is infinity. We found that the integral for, okay, this one is convergent, which is good, but this one equals to infinity. This makes automatically this integral is divergent. Okay, we have a note. Riemannian interval is finite. The integrated function is continuous. Both are plus. First type, improper integral, here is minus, here is plus. The second type, improper integral, here is plus, here is minus. And third type improper integrals are integrals whose neither interval is finite nor the integrated function is continuous. And you may observe these integrals by yourself. We will continue the topic of vector valued function in our next video.